Okay, so welcome back. So now in this video we're going to start talking about what's called quadratic factors. So far we've talked about linear factors and how do we deal with distinct linear factors, how do we decompose it if we have repeated linear factors. So now we're going to talk about irreducible quadratic factors. Okay, so first we're going to talk about distinct irreducible quadratic factors, and then we're going to talk about repeated irreducible quadratic factors. But the question that we should start with is, what is a irreducible quadratic factor? And quite simply, it's a factor that, it's a quadratic factor that cannot be factored any further using real roots. What do I mean by that? So we can usually, when we factor polynomials, we factor them into until we can't factor them anymore, right? And so we are usually talking about real roots, real zeros, okay? So, but if we talk about complex zeros, we can factor things using complex zeros, but in this case, all we care about are the real zeros. So just our normal ways of factoring things. So if we factor something and it's a quadratic expression, a quadratic polynomial that cannot be factored, meaning it has no real zeros, okay, then it's called irreducible, okay? And those are the factors that we're talking about here. So this quadratic expression, this quadratic function, or quadratic polynomial is irreducible if we can't factor it, okay? And so in that case, what do? So I'm going to show you the decompositions involving irreducible quadratic factors. And the first thing we're going to do is we're going to talk about simple quadratic factors. We're going to talk about distinct first. We're going to talk about distinct quadratic factors, and then we'll talk about repeated quadratic factors. Okay, so let's use this as an example. Okay, so if we factor this, first of all, notice that the denominator, the degree of the numerator is less than the degree of the denominator, so we're good there. So now we're going to factor this, and so we're going to rewrite this as 2x minus 3 over x times the quantity x squared plus 1. Now, notice that we have got two factors. This one is a quadratic, and it's irreducible because we can't factor a sum of two squares. If it was a difference of two squares, that'd be one thing. We could factor that all day long. This is a sum of two squares, so there are no real roots, real zeros for this. So that means, what do we got? Well, we've got a linear factor, this x. Remember, this is the same as x plus 0, right? So don't think that this is quadratic. Even if it was x squared, okay, even if I put a square up here, it's still a linear factor because the way you want to think about this is x plus 0 squared. Okay, so it's a linear factor. So keep in mind, any factors of this type where it's x or x squared or x third or x to the nth power is a linear factor. Okay? Just keep in mind, that's a common mistake that students will make. Okay, so now I've got this x here, and I've got this quadratic here. So I know how to deal with this. How do we deal with this? Well, this is an irreducible quadratic factor, so this is the decomposition you need. Okay, if it is a quadratic factor of this type, okay, where it's let me do this. So we know how to deal with this, right? This is going to be a over x, because it's a linear factor. But what about this quadratic? Well, the way we're going to handle these is we're going to have a linear term on the top. And so to deal with this one, we're going to have bx plus c over x squared plus 1. So in other words, when we're dealing with linear factors, we have a constant on the top. When we have irreducible quadratic factors, we're going to have a linear expression on the top of ax plus b, or in this case, bx plus c, since we're already using a over here. Okay, now we're done. Now I've got this one and this one. Okay, and so now we just have to do the same thing. Solve for the constants. So let's do our scratch work. Okay, so now let's set up our equation. So this is going to be 2x minus 3 is equal to a times x squared plus 1 plus bx plus c times x. Okay, so now, well, how do we solve this? Well, this is going to be tricky since no values of x will get rid of this, right? So this we can't get rid of. If we make x 0, okay, there's no way to get rid of that. So, but if we make x 0 here, this goes away, this becomes a, this becomes 0, well, this whole thing becomes negative 3, right? So we get a equals negative 3. So we got that one by doing our strategic substitution, right? So if we make x 0, this goes away, this becomes 1, 1a, so that becomes a equals negative 3. So if x equals 0, a equals negative 3. Okay, so we got that one. Okay, now, if a equals 3, or excuse me, so if a equals negative 3, let's plug that in. So, we've got 2x, hold on, let's put in negative 3 here. Okay, so let's do x equals 1. Well, if we do x equals 1, we're still going to get the system of equations. We need to solve for one more. So you know what I'm going to do? I'm going to set up the system of equations here. So what I'm going to do is I'm just going to I'm going to solve this, even though I know x is equal to negative 3. We'll plug that in a minute. So let's simplify this. So this is 2x minus 3 equals negative 3x squared plus negative 3 okay, and now I'm going to rearrange things so we know that 2x minus 3 equals, well, we got b minus 3x squared, and then we got plus cx minus 3. Well, guess what? this has to equal 0. So we know b minus 3 equals 0. And we know c has to equal 2. And we already got the negative 3, which confirms what we had before, right? So guess what? This means that b equals 3 and c equals 2. And we're done. Okay, now we're ready to evaluate. So our scratch work is done. Okay, can't forget our integral. Okay, now we should know how to do this. So this is going to be 3 times the natural log of the absolute value of x. Okay, so now this one we're going to have to decompose. Or not decompose, but split up. So this we're going to write is two different terms. We're going to split it up into 2 different fractions. Okay? Like so. Okay. So far, so good. Oh, what am I doing? 0. Sorry. This is +1. There you go. Okay. Okay, so now this one here is a u substitution. And this is really just du over u. So again, we pull the 3 out, right? And we're going to get a 1/2 here. So again, do your u substitution. Okay? So again, if this is your u, your du is going to be 2x. You're going to pull the 3 out, but then you're going to have you'll have to have a 1/2 in here. Okay? So if you do that, then you're going to get plus. So pull the 3 out. So it's going to be 3, and then it's going to be x over x squared plus 1. And so here, let me just write it out. So u equals x squared plus 1. Your du is going to be 2x, but then you're just going to divide by 2. And so now you get this, and so you're going to get another 1/2 out of here when you do your substitution. So then it's just going to become, it's going to be du over u. 1/2 du over u. So that means we're going to get 3/2. And then it's going to be the natural log of u, which is x squared plus 1. So that's going to be the next term. And then this one here, you pull out the 2, right? And what does this turn out to be? Well, 1 over, or dx, right? Dx over x squared plus 1 has the form of du over what? or not u, but a squared. Which the integral of that, you should know, is inverse tangent. So this is going to be tangent inverse of x plus c. And that's the end of it. And that's it. So just make sure you pay attention to the integrals that you have. Oh, by the way, here we could drop the absolute value signs, right? Because there's no way that this can be negative, right? So we're okay. So the domain of this is okay. Here we can't. So, but in this case we can, because it will never have a negative inside the log. Okay, that's it. We'll do another one. Take care.